So what we were talking about until now is that light is a wave, but light also behaves like a particle, which we call the duality of light. It's both a wave and a particle. And the photoelectric effect proved that light is also a particle. And the question had to be made, well, if light can be both, can matter be both, right? Can matter also be a wave? And remember that we found that there is a way to find, using equations, the wavelength of matter, right? We won't prove this again. We just have to remember this. This is not in your physics booklet, so you have to know this by heart, right? So now the thing is, we have to test this, right? We should test if particles also behave like waves. How could they, right? They're just particles. So they got this experiment. They say, okay, this should be the wavelength, right? It depends on the momentum, right? So normally objects are too big because they have too much mass. If they have too much mass, the momentum is too big, right? And if momentum is too big, the wavelength is too small. In order to be able to measure something with a wavelength, you have to have a relatively large wavelength, right? That is measurable. Planck's constant even is very, very small, right? So you have to have a very small object. And what better object than an electron? It's probably one of the easiest to manipulate. Being very light, has a small momentum. So it should produce, in theory, a wavelength that we have, that we are able to measure, right? And here comes the Davison-Germer experiment. And it was an accident, right? So they were doing experiments on nickel crystals. And what they were doing is, well, they have an electron gun, right? So there's an electron gun. It emits electrons at a certain direction with a certain amount of energy, right? In this case, it says there's graphite in there. This is a different experiment, but just to illustrate where the electrons came from. And if you look at the experiment, you have an electron beam coming in, right? And this beam is directed at nickel, right? And it would bounce off. What you would normally expect is if you shoot electrons at anything, they're just balls, right? If balls bounce off other balls, which are the atoms, they should scatter randomly. It's just bouncing off a sphere, right? It depends on how it hits it. It goes in a different angle. So you shouldn't have any peaks. You shouldn't have any maximums or minimums, right? They should just be random bouncing. That's what they expected. But what they got is when they measured this, certain directions had peaks, right? So it bounces. This detector is able to be moved any direction, right? Any angle. So they moved at different angles, and what they expected is just, normal random distribution, right? That you expect, but no. What happens is at certain directions you have big peaks, right? And the only way you can have peaks is if you have interference. If you have done waves before this class, and you probably have, you know that there's double slit interference, there's multiple slit interference, right? So what they found was, if you look at the atoms, right, the atoms are a certain distance apart, all of them. The electrons will bounce off of them, right? But instead of bouncing in this particular direction that is random, what they will do is it spreads like a wave, right? In all directions. So these are like slits, and you can treat this exactly like multiple slits, right? So at different angles, they're going to have a different path difference, and you're going to have different intensities. So if you have slit distance is d, then the path difference is going to be d sine theta, right? And the constructive interference condition says that, well, when the path difference is equal to n theta, you should get constructive interference, you should get a peak. So only at certain angles you get peaks. And that is exactly what they got. The electrons were bouncing off the atoms, but they were not bouncing like you expect in random directions. They bounce like you get waves. Waves that have the bounce off the atoms look like multiple slit interference patterns. And this proved that matter also behaves like waves. They're also dual. They're not just particles, they're also waves, right? And when they measured the angles based on the wavelengths, they found that the wavelength is in fact the velocity, right? Planck's constant divided by the momentum. Which is very easy to find. If you know the kinetic energy of the electrons, you know what the momentum is going to be very easily, right?